So in the previous lecture, we were discussing regarding the integration, and I have asked you some questions regarding the differentiability. So under the convergence, whether each fn's are differentiable, can we say that f is integrable? The second question is, can we interchange the summation and the differentiation sign? And the third question is, can we interchange a limit and a derivative sign whenever it is required? So these are the few questions I have raised in the previous lecture. Here I am giving you a counter example for each one of these. So first example that I like to give for this, that means we cannot interchange the limit and the differentiation sign. So for that, consider this sequence of functions, that is fn of x is equal to sin nx upon root n for x belongs to R. We'll first prove that this fn is uniformly convergent, and then we'll prove that this cannot be possible to do. So if you want to prove that this is point-wise convergence, we just note that sin nx upon root n is always less than or equal to 1 upon root n, due to the sine function is always less than or equal to 1. And this is always greater than or equal to 0. So we note this. We already have this thing. And if you take the limit both sides, then by sandwich theorem, we can say that limit of n tends to infinity sin nx upon root n is 0, because this is tends to 0 as n tends to infinity. So we'll have this. So ultimately what we can say is fn converges to f pointwise due to this as n tends to infinity. Now let us prove this is uniform convergence also. So to calculate the uniform convergence, you need to find out what is Mn, which is a supremum of mode of fnx minus fx, as your x is belongs to R. But what is fx is sin nx upon root n minus fx is 0 as x belongs to R. And we know that the supremum of this one is whatever the supremum is this. It depends on sin nx, and supremum of sin nx is 1, because sine function is always between -1 to 1. So this is the supremum of sine function. So this is a square root of n, that we can definitely say. If you want, you can just prove by taking your gx function as sin nx upon root n, then calculate g dash of x equal to 0, and implies whatever the points you will have, put it into this g and find out g double dash of x. Whenever on that point we'll have a negative value, we'll have the value, its supremum. So then that way you can calculate the supremum of sin nx upon root n. But I'm just saying that the supremum of this one is 1 upon root n due to this reason which I already given. And this will tends to 0 as n tends to infinity. So we can say that the fn converges to f now uniform as n tends to. So this convergence is uniform convergence. Now let us see whether we can interchange the limit and the integration sign. So for that, I have to find out what is the derivative of the function fx. The function f is sin nx upon root n. So the derivative of this one with respect to x is cos nx upon root n into n. That is equal to root n into cos nx. Now, if I take limit of fn dash of x as n tends to infinity, that is the limit of root n into cos nx as n tends to infinity. And this function cos nx is a bounded function, and n goes to infinity as this n tends to, so root n goes to infinity. So this will have the answer infinity. On the other side, what is f dash of x? Fx is 0 for all x belongs to R. So this will imply f dash of x is also 0 for all x belongs to R. So that means a limit of n tends to infinity, f dash of x will be 0. So ultimately what we got is this, that this quantity, that is the limit of n tends to infinity d by dx of fn of x. This side is this, which is infinity, which is not equal to a d by dx of a limit of n tends to infinity fn of x dx. Because this side, this one is 0 due to this, fx is 0, and d by dx of 0 function is 0. So this side is 0 and this side is infinite. So in general what we can say is this limit and the integration, limit and the differentiation is cannot be interchangeable even though the convergence is uniform. So under the uniform convergence also we cannot interchange this limit and the differentiation sign. In the integration we have already proved for that limit and the integration sign can be interchanged under the uniform convergence, but cannot be done for the differentiation. So the reason for this one we already got, that is the last thing. That means under the uniform convergence this statement is not true. Obvious question one can ask is, then what should be the condition in which this is true? The next question is, each fn's are differentiable. Can we say that f is also differentiable? So for that we'll discuss the next example. So this is the example that I'm talking, that let fn x, if I define by mod x power 1 upon 1 plus 1 by n, as your x is belongs to minus 1 to 1, then prove that or show that the first one, fn is belongs to d of minus 1 to 1. D of minus 1 to 1 I already talked that it is a differentiable function over upper interval minus 1 to 1. Second statement is fn let us write that example again here. Let fn x is equal to mod of fx, f mod of x plus 1 by n, x belongs to minus 1 to 1, and so that first one, fn is belongs to dab, that is minus 1 to 1. DAB is a set of all differentiable function from minus 1 to 1. The second is fn converges to f. The f is mod of x uniformly on minus 1 to 1. And what is this tells you that fn converges to f mod of x, but this mod of x is not differentiable. The third statement is not belongs to d of minus 1 to 1. That we know already, that mode function is not differentiable in the interval -1 to 1 because it's not differentiable at 0. So this statement or this example tells you that each fn's are differentiable, but its limit may or may not be differentiable, even though the convergence is uniform. Again, one can ask the question under which situation it will be true. Okay, so let us try to discuss the proof of or solution for this example. So we have to prove here that each fn which we have defined here are differentiable functions. So obviously, if I want to prove that this is a differentiable function, if I can prove for positive x, then the same proof will work for negative also. A slightly modification is there. But if x is positive, then this is x power 1 plus 1 by n is there. Actually, this function is like this. Fn x is this x, sorry, x power 1 plus 1 by x if x greater than 0, minus x raised to 1 plus 1 by n if x is less than 0, and 0 if x is equal to 0. And if x is positive and x is negative, this function is automatically differentiable. Only the problem is occur at x is equal to 0. So we'll prove that at x is equal to 0, the function is differentiable. So it is, we note that x is greater than 0 or x is less than 0, fn is differentiable. Now we shall prove the result, or the function is fn, each fn's are differentiable at x is equal to 0. So for that I need to looking at what is 0 plus h minus fn at 0 upon h. That is a definition of a differentiable function, x plus h minus f of x upon h as h tends to 0. We have to looking at this thing. So this is the things fn 0 because x equal to 0, at 0 we are discussing this. This is equal to mod h raised to 1 plus 1 by n, because 0 plus h is h minus 0, fn at 0 is 0 upon h. This is mod h 1 plus 1 by n upon h. That can be expressed in this manner, that this is if h is positive, then this is h power 1 plus 1 by n, and if h is negative, then this is negative sign comes here also, so that is minus of minus h raised to 1 plus 1 by n if h is less than 0. Now if I take the limit both side, n tends to infinity, sorry, h tends to 0. If I take the limit h 0 plus h minus fn at 0 upon h, then this limit of this function will be limit of this, and if h is positive, so there will be two way you can go, either h plus sign, that means right hand limit will gives you 0 answer, left hand limit is also gives you 0 answer. So therefore the limit of this one is 0, and hence we can say that at n is differentiable at x is equal to 0. So ultimately we can say that Fn belongs to minus d of minus 1 to 1. That means it is differentiable. So we have proved the first one. Now second, to prove the second one, we have to looking at what is the supremum, because here we have a sequence. Fn is a sequence of function. So to prove that it is uniform convergence, you have to find out Mn. Mn is the supremum of Fnx minus Fx. So for that I can define now Sn of x, which is mode of Fnx minus Fx. So ultimately I have to find out what is the supremum of this function. But what is Fnx, which is mode of f plus 1 by 1 upon n minus mode of x. Now what is this function? If x is positive, then this function is x minus 1 plus 1 by n. If x is 0, then this is 0 function. And if x is negative, then this is minus x minus of minus x 1 plus 1 by n. Because it is a mode function. Okay, so that's why we can have this quantity. And if you want to calculate the maximum or a supremum of this function Sn of x, then you have to find out its derivative. Derivative equal to 0. That you have to do. Okay. So let us see what is Sn dash x. So as per this, the derivative of this one, it is 1 minus 1 plus 1 by n x power 1 by n if x is positive. If x is 0, then it is 0. And if x is negative, then it is minus 1 minus 1 plus 1 by n minus x raised to 1 plus 1 by n minus 1, so that is 1 by n. And the derivative of minus x will become minus 1, so that's why we are plus if x is negative. So now we have to calculate the stationary points if Sn dash x is equal to 0 implies. So first that I need to take what is x is greater than 0. What will happen? If x is greater than 0 and Sn dash is equal to 0, then this will give you 1 minus 1 plus 1 by n x power 1 by n is equal to 0. So that will give you x power 1 by n is 1 upon 1 plus 1 by n. And if you take the power n both sides, then this is x equal to 1 over 1 plus 1 by n whole power n. So this is the quantity, or this is the things, these are the stationary points. If x is greater than 0, then Sn dash of x equal to 0 will implies minus 1 plus 1 by n minus x raised to 1 by n equal to 0. This will implies minus x raised to 1 by n equal to 1 upon 1 plus 1 by n. Therefore, this will give you x is equal to minus 1 upon 1 plus 1 by n whole power. And x is equal to 0, then x is 0. So that is, there are three stationary points is that. The first one is this 1 minus 1 plus 1 by n raised to n. Another one is this minus 1. So I can say, and 0. That is the third form. And we have to see at this value what is the Sn double dash of x. And how to calculate the Sn double dash of x? By taking the derivative of this. If x is positive, then a derivative of this one is 0, and this 1 by n is come down, so it is minus of 1 plus 1 by n, 1 by n into x power 1 by n minus 1. If x is equal to 0, the things is 0. If x is negative, then again the derivative of this quantity, the last term, that is minus 1, the derivative of this. Minus 1, derivative of minus 1 is 0. This 1 by n come down, and the derivative of minus x is minus 1. So this again 1 by n is down, 1 plus 1 by n, x raised to minus x raised to minus 1 by n, and the derivative of minus x is minus if x is negative. And one can note that if Sn dash double dash at the point 1 upon 1 plus 1 by n power n, if I can substitute the value of x here, then this is negative. Okay, so this is a negative. So we can say that it's having, and this is also negative. So I can just write down plus or minus instead of plus, because both of this value gives you negative. So therefore this is the things we got, and from this we can say that the Snx attains its maximum at x is equal to plus or minus 1 upon 1 plus 1 by n power n. So this is the things we got, that we can say, and from this we can find out what is Mn. It's not working. Let me do it here. So what is Mn? Mn is the supremum of Sn of x, as your x is belongs to minus 1 to 1. But the supremum of Snx is nothing but the Sn at 1 upon 1 plus 1 by n power n. So, and what is the Sn? This is the positive value I have taken. So the Sn at this value which we have calculated is this x minus 1 plus 1 x power 1 plus 1 by n. So that's why we'll have, that is x minus x is this, that is 1 upon 1 plus 1 by n power n minus 1 over 1 plus 1 by n power n and whole power 1 plus 1 by n. So this we can write down, this first things is as it is. The second one I can write down in this fashion, that is 1 upon 1 plus 1 by n power n into 1 upon 1 plus 1 by n. Due to this power 1, this is power 1, this quantity is power 1, and this is power 1 by n whole power n, so that will, and this will times 2. And we know that it is 1 plus x power 1 upon x will tends to e as x tends to infinity, so x tends to 0. Is the same manner this will tends to 1 upon e. This is also tends to 1 upon e, and this will tends to 1. So that is 1 minus 1 upon e minus 1 upon e is equal to 0 as n tends to infinity. So it's conclude that is mn is converges to 0. So hence we can say that this fn x or fn converges to f uniformly as n tends to infinity, and which proves that each fn's are differentiable, but f is not differentiable under the pointwise convergence, and even though in the uniform convergence. So the question is, under which situation it will be true. A third one is the proving that mode of x is not differentiable. I think so everyone can do it, able to do this at this stage, that mode of x is not differentiable at point 0. That I am giving you as a homework to do it yourself. So ultimate goal of this lecture is to discuss certain examples that uniform convergence is not preserving the differentiability. So the next question one can ask is, under what situation it will be true? That means under which situation, if each fn's are differentiable, then f is also differentiable. That is interesting question to ask and to find out the answer to this question. We'll discuss this answer to this question in the next lecture. If you have any doubts, then you can ask.